Welcome back to this session. I am Dr.R.RADHIKA from S.A.ENGINEERING College, Department of Electronics and Communication Engineering. In this section, we are going to discuss about DTFT and DFT. This is part of the syllabus in GATE, that is Section 2, Networks, Signals and Systems. This comes under Discrete Time Signal Processing. Now we are going to discuss about what is a signal processing. Humans are the most advanced signal processors. Speech and pattern recognition, speech synthesis, these things comes under signal processors. And we encounter many types of signals in various applications. Electrical signals, voltage, current, magnetic, electric fields. Mechanical signals such as velocity, force, displacement. And acoustic signals, sound, vibration. The other signals are pressure and temperature. These things are discussed processed under signal processing. And then the most real-world signals are analog signals. In signal processing, there are two types of signals. One is analog signal, another one digital signal. Most of the real-world signals are analog signals. They are continuous in time and amplitude, convert to voltage or currents using sensors and transducers. Analog circuits process these signals using resistors, capacitors, inductors, amplifiers. Analog signal processing examples are audio processing in FM radios, video processing in traditional TV sets, because nowadays we are going for digital signals. So video processing in traditional TV sets. What are the limitations of analog signal processing? Accuracy limitations due to component tolerances, undesired non-linearities, and then limited repeatability due to why the limited repeatability is limited in this case means due to tolerances and changes in environmental conditions, that is temperature and vibration. Sensitivity to electrical noise. This is also one of the limitations, disadvantages of analog. And then limited dynamic range for voltage and currents. Inflexibility to changes. It is not flexible. Difficulty of implementing certain operations, that is non-linear operations and time-varying operations, and then the difficulty of storing information, because analog signals occupy more storage environment. And then what is digital signal processing? The limitations in analog signal processing is overcome by digital signal processing. In digital signal processing, we get a real world signals as an analog signal. This analog signal is converted to digital with the help of A to D converter, and then the digital signal is processed in digital signal processing. We get a digital signal. Digital signal is again converted to analog signal and given output. Represent signals by a sequence of numbers. Sampling or analog to digital conversions. This comes under A to D part. And then we perform processing on these numbers with a digital processor, that is a DSP, digital signal processing. And then reconstruct analog signal from processed numbers. Reconstruction of digital to analog conversion, that is D to A, we get an output as an analog signal. And then there are two types of signals. One is analog, another one digital. The analog signal may be an input, we get an analog output. The example for this, digital recording of music. Analog signal is an input and digital signal as an output, that is touch tone phone dialing. And then digital input, analog output. Text to speech. Text is in the form of digital, and then speech is in the form of analog. Digital input, digital output. Compression of a file on computer. This is an example for digital input and digital output. Digital signal processing. Analog signal is converted to digital with the help of ADC and then processed in a digital signal processor. In this, the input is a digital signal. It is processed in this processor and get a digital output. This digital output is given as an input for this DAC converter, and then the digital signal is converted to an analog signal. The advantages and disadvantages of digital signal processing. Pros: accuracy can be controlled by choosing word length. So accuracy can be controllable, and then repeatable. Sensitivity to electrical noise is minimal. Dynamic range can be controlled using floating point numbers. Flexibility can be achieved with software implementations. Non-linear and time-varying operations are easier and implement. Digital storage is cheap. Digital information can be encrypted for for security, price and performance, reduced time to market. And then cons of digital signal processing, sampling causes loss of information because the analog signal is converted to digital with the help of a sampling process. And then A2D and D2A requires mixed signal hardware, limited speed of processes, quantization and round off errors occur in this digital signal processing. Then what is called a signal? A signal is any real world quantity varying with other references like time or space. We commonly come across different types of signals: acoustic signals like speech and audio, spatial signals like image and video, biomedical signals like ECG. The purpose of signal processing is to understand signals and extract useful information from them. While doing so, signals may have to be converted to different forms to facilitate their analysis, processing, storage or transmission. For example, a piece of music may be converted to electrical form for transmission or may be stored on a magnetic media. So this is a temporal signal example. We get a signal like this and then it is converted to an electrical form. And then this is spatial signals. With the help of the sampling and quantization, we can get it. X, Y. So discrete time signal sequences. Discrete time signals are represented by a sequence of numbers. This is an analog signal. It is represented in a discrete form. The nth number in the sequence is represented with X of n. Often time sequences are obtained by sampling of continuous time signals. So you get a sampling of continuous time signals. In this case, X of n is value of analog signal at XCNT, where T is the sampling period. The continuous signal is converted to in the discrete forms with n samples, and then x-axis is represented in T. T means continuous time, it represents to time. Basic sequences and operations in digital signal processing. Delaying, the first operation, we call it as shifting a sequence. Y of n is equal to x of n minus n naught. That is a delay n minus n naught. So we call it as delaying a sequence. And then unit samples impulse sequence. Unit sample and impulse sequence is represented as del of n, that is equal to 0 when n is not equal to 0. 1, n is equal to 0. See here, n is equal to 0, we get an output as 1. The remaining things, the output is 0. Unit step sequence we represented as u of n. N is less than 0, the output is 0. N is greater than or equal to 0, the output is 1. See here, n is less than 0, output is 0, and then 0 or more than 0, the output is 1. Exponential sequence, x of n is equal to a alpha of n. So this is in the exponential format. Discrete time systems. Discrete time sequence is a mathematical operation that maps a given input sequence x of n into an output sequence y of n. So y of n is equal to t of x of n. So x of n is an input. There is a mathematical operation which is represented by t. We get an output y of n. Example, discrete time systems example is moving, average, running. So y of n is equal to x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3. This is moving a sequence. And then maximum, from this maximum of x of n minus 1, x of n minus 2, we can able to identify. Ideal delay system. So y of n is equal to x of n minus n naught. This is a delay. And a memoryless system. A system is a memoryless system if the output y of n at every value of n depends only on the input x of n at the same value of n. Example for memoryless system, square. Y of n is equal to x of n square. Sine. Y of n is equal to sine of x of n. The example for ideal delay system is y of n is equal to x of n minus n naught. So these things are comes under memoryless system. And then when the system is called it as a linear system, we know that if the system is satisfying the superposition principle, we call it the system as a linear system. So a system is linear if and only if it satisfies t of x1 of n plus x2 of n is equal to t of x1 of n plus t of x2 of n. So that is t of a x1 of n is equal to a t of x of n. This is called scaling. And then ideal delay system, y of n is equal to x of n minus n naught. We know that. So t of x1 of n plus x2 of n, we apply this law, we get x1 of n minus n naught plus x2 of n minus n naught. T of x2 of n plus T of x1 of n minus n naught plus x2 of n minus n naught. T of a x of n is a x1 of n minus n naught. This is scaling. A T of x1 x of n is equal to a x1 of n minus n naught. So both left hand side and right hand side are equal. So the systems comes under linear system. Then the system we call it as a time invariant system. It is the system is not varied with respect to time. Time invariant system, shift invariant system. The time shift at the input causes corresponding time shift at the output. So this is y of n is equal to t x of n. Y of n minus n naught. That is we introduce a delay here. We get t of x of n minus n naught. So we call it as time invariant system. And then example as in square, y of n is equal to x of n square. Delay the input, the output is y1 of n is equal to x of n minus n naught square. So delay the output gives y of n minus n naught is equal to x of n minus n naught whole square. So similar example, compressor system, y of n is equal to x mn. So delay the input, the output is y1 of n is equal to x of n minus n naught. In the output, y of n minus n naught means x of n minus n naught. So this is time invariant system. Another one is causal system. Causality. The system is causal. Its output is a function of only the current and previous samples. So it depends only on the current and previous samples. And then the system we call it as a causal system. So examples, backward difference, y of n is equal to x of n minus x of n minus 1. And then this is current and previous. Forward difference, y of n is equal to x of n plus 1 plus x of n. So this is x of n plus 1 is a current one and x of n is the previous sample. And then DFS, DTFT and DFT. We convert the time domain into frequency domain. We go for transformations. So there are DFS, DTFT and DFT are there. And then Fourier transform of continuous time signals. X of f is Fourier transform of x of t, that is integral minus infinity to infinity x of t e power minus j 2 pi f t dt. X of t is equal to inverse Fourier transform means x of f, that is equal to minus infinity to infinity x of f e power j 2 pi f t dt. And then this is linear time invariant system and Z transform. So x of n, h of n, y of n. So y of n is equal to x of n convolution of h of n. So we call it as summation m is equal to minus infinity to infinity h of n x of n minus m. If the impulse response has a finite duration, the system is called finite impulse response FIR. So this is a finite value. And then Z transform, x of z is equal to z x of n, that is equal to summation n is equal to minus infinity to infinity x of n z power minus n. So x of n h of s y of n, that is y of z is equal to h of z into x of z. Frequency response of a filter h of f is equal to h of z is equal to e power j 2 pi f. And then signal processing methods. What are the methods involved in this process the signal? So with respect to periodicity and time, we classify that continuous and discrete time, periodic and aperiodic. Duration is finite, infinite. If there is a continuous and periodic, we go for Fourier series. Continuous, aperiodic, continuous time Fourier transform. Discrete, periodic, DFS, discrete Fourier series, and discrete, aperiodic, discrete time Fourier transform and Z transform are used for the conversions. And then four Fourier methods, that is continuous time Fourier transform is used for continuous time and continuous frequency, and continuous time Fourier series is used for discrete frequency and continuous time. Discrete time and Fourier transform is used for discrete time and continuous frequency. Discrete Fourier transform is used to convert discrete time and discrete frequency. Discrete time is converted to discrete frequency, we go for DFT. Discrete time is converted to continuous frequency, we go for DTFT. See the relationships among the Fourier methods. This is from CTFS and CTFT, DFT, DTFT. Aperiodic continuous means we go for Fourier transform. So this is a formula to convert the continuous to the frequency domain, and then Fourier series. Periodic continuous means we go for Fourier series. This formula is used to convert time domain to frequency domain. And then periodic discrete means we go for DFT. So this formula is used to convert time domain to frequency domain. X of k is summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi by n in k. And this is number of things, this is a current sample. X of n is 1 by n, this is inverse DFT, 1 by n, summation n is k is equal to 0 to n minus 1, x of k e power j 2 pi n, 2 pi by n by nk. This is minus, this is plus. Discrete Fourier transform. DFS, discrete Fourier series, provided as a mechanism for numerically computing a discrete time Fourier transform. But most of the signals in practice are not periodic because it is in continuous nature. They are likely to be a finite of length. Theoretically, we can take care of this problem by defining a periodic signal whose primary shape is that of the finite length signal, and then using the DFS on this periodic signal. So most of we concentrate on periodic and then we continue the process. Practically, we define a new transform called the discrete Fourier transform, which is the primary period of DFS. So this DFT is ultimate numerically computable Fourier transform for arbitrary finite length sequences. And finite length sequences and periodic sequence. This is finite length sequence that has n samples, periodic sequence with a period of n. This is window operation, and this is periodic extension operation. Then aperiodic discrete, that is a DTFT. So this is the formula to calculate DTFT, and then this is a formula to calculate DFT and IDFT. Now we enter into a practice question. These questions are asked in previous year GATE question papers. So first question is, let an input x of n having a discrete time Fourier transform x of e power j omega, that is 1 minus e power minus j ohm plus 2 e power minus 3 j ohm, be passed through an LTI system. LTI system is linear time invariant system. The frequency response of an LTI system is h of e power j ohm, that is equal to 1 minus 1 by 2 e power minus j 2 ohm. The output y of n of the system is, there is an option. So there is a property, that is in a time domain we go for a convolution. In frequency domain means we go for multiplication. So x of n convolute with h of n is equal to x of e power j omega multiplied with h of e power j omega. So in this case, x of e power j omega and h of e power j omega is given in a frequency response format. So we can multiply these things, we get a frequency domain output y of e power j omega. Then we convert that into y of n, take the inverse. We get an output as C. Discrete time signal x of n 1, 2, 3, 0, minus 3, minus 2, minus 1 is having a discrete time Fourier transform x of e power j omega. The value of integral minus pi to pi x of e power j ohm whole square d ohm is 28, 28 pi, 56 pi and 14 pi. So in this x of e power j omega, the value is integral minus pi to pi x of e power j omega whole square d omega. So in this value is integral minus pi to pi x of e power j ohm square. So we can apply this, we get an upper limit pi minus the lower limit minus pi and then square. So 1 square plus 2 square plus 3 square plus 0 plus minus 3 whole square plus minus 2 whole square plus minus 1 whole square. We get 28. From this is pi, minus of minus pi is 2 pi. 2 pi into 28, that is 56 pi. So the answer is 56 pi. You can check it. So the answer is 56 pi. Then the inverse DTFT, the limits of the integral is defined between minus pi to pi because of the property. So minus pi to pi, we go to the property periodicity. And then h of e power j omega is the frequency response of a discrete time LTI system, and h1 of e power j omega is the frequency response of its inverse function. See here, frequency domain and frequency response of this. H of e power j omega is multiplied with, because both are in frequency, so h of e power j omega is multiplied with h1 of e power j omega, that is equal to 1. So the answer is 1. Thank you. We'll see you in the next video.